Today I'll be speaking on some of the engineering challenges we faced for a heavy industrial structure in a power plant. And my talk coverage will be I'll give you the overview of the steel structures in power plant, because power plant takes a lot of loads from piping, equipment. So steel is obvious choice, and I'll just brief you what are the structures. Why we select the steel, some glimpse of that. I'll take the case study of a turbine building, which is about 14,000 metric ton structural steel, housing a lot of piping, equipment, cables and everything. And I'll be speaking mainly on what are the changing trends in construction in power plants, and how engineering companies and structural designer like us have to handle this type of issues, or the things which are coming new are being addressed. I'll close my session with some remarks. So I belong to a company called L&T-Sargent Lundy, which is a joint venture of Larsen and Toubro and Sargent Lundy, which is about 125-year-old company in power industry. We operate from Baroda. We are about 450 people, and then we have a combined experience of about 60,000 megawatts of power, both in the Indian market and in foreign. So if you can see the steel structures, so one of the biggest structure is boiler here. Okay, so in a 3-unit project, you have 1, 2, and 3 boiler. Connection between boilers with galleries. This is a turbine building about 300 meters long for a 3-unit. We have a lot of pipe racks which runs in kilometers, maybe 3.5, 4, 5 kilometers based on the layout. And of course, there is equipment called ESP, which is also supported using steel. So steel is everywhere in power plant. When you enter a power plant, steel is everywhere. Okay. Now, why we choose steel? Okay, the prime reason is basically for taking care of the heavy loads. If I speak about piping lateral loads, okay, which is induced by 100 mm thick 600 dia pipe, which may force in lateral direction force up to 50 ton per support. So we many times design the turbine building long bracing for total of 250 ton, 300 ton of lateral loading. And resisting is such a huge force, and concrete is never a choice. Apart from that, we have to handle with large spans, 33-meter TG hall is always there, which houses about 2 cranes of 125 ton, sometimes 350 ton. Okay, to take care of such things, we have to use steel. Of course, we need more room for electrical and mechanical services. Nowadays, client wants the entire plant to be very compact, and they have to house a lot of things within a short space. Earlier, what I can say is a 660 megawatt project would use 36 meter width of the building. Now it has come to 30 meters. So you can understand about 15% saving in the width has happened over last 6 to 7 years. Pipe rack, as I said, it will be decided at a later stage. A lot of things will be supported from that. A lot of building will be required. And for the speed of erection and construction, obvious choice is the steel. Okay. So I'll take example of a supercritical project turbine building, which will be about 19 meter in overseas plants versus 125 meter per unit in domestic condition. Width, as I said, is about 30 to 33 meter. Heater bay, what we call, is housing a lot of heavy equipment, is about 12 to 14 meter. Building height ranges from 36 meter in some places to 42 meter in other places. Column spacing generally is 10.5, 11, 12. So you can imagine the columns are spaced at about 10 to 12 meter. Step columns are of course required. The depth of column ranges between 1500 to 2 meter. So you can imagine what challenge for a structural engineer will be to save the material. Of course, this particular thing is a plant. So earthquake load is going to create a lot of issues for a structural engineer. The masses are not uniformly distributed like in a commercial building or in a residential building. You will have a corridor of piping equipment in one place and empty space on other space. So it's a big challenge to make structure behave properly during the earthquake conditions. And typical engineering cycle is about 12 to 18 months. And usually, structural steel, we are proud to say that we are one of the most economical in designing this kind of plants with 12,500 to 30,500 ton, whereas our competitors design in like 15,000, 16,000 ton. So, I mean, this is a three-dimensional view of TG building from outside. And if I can show you something inside, what it houses actually, you will see like say a lot of equipment at very high level, like say, this light is not working. Yeah. So this top cyan colored item is about like 600 ton equipment sitting at 31 meter. You will see a lot of piping, like say this silver color things are piping, which is like say 100 thick, 600 die. You can imagine what is the weight it is going to induce. Carrying like say the steam with a temperature of about 600 degrees centigrade under 250 bar pressure. So quite heavy loads which will be induced from piping. And you can see here that the space on the other side of the piping is completely empty. Okay, so you will have a lot of concentration of load here. You can see two cranes running in tandem. Typically, as I said, 125 to 300 ton. Now, what is the challenge for an engineer? Because this type of buildings will be like say constructed in like say anytime between like say 26 months to 30 months. Okay, and the construction as well as erection of equipment happens into the stages. So when like say we allow the crane to be tested, okay, it has to be designed for this type of loads induced because of the crane testing. Okay, while the building is not complete, it is subjected to the loading. So we have to run multiple analysis to take care of like say erection condition or like say construction condition and likewise. Now see the building frame as you can see here. This particular photo is from the recent photograph from bolted structure. Previous one which I showed was from the builded construction. And in order to maintain like say the space for utilities and other things, you will see in the top gutter we have made some holes. It's actually plate gutter of 2.5 meter deep. Okay. But in order to maintain the weight for the logistics and to save on the material part, we have created like say openings from the gutter. It is not a castellated beam, which is very commonly used, but it is made in such a way that it carries the weight. Truck load is also maintained in a very, very economical way. So I'll just speak about like what is the traditional approach we have seen. I mean, my experience goes way back in '95, where we used to design concrete buildings for a small plant, steel building of course for a big plant, but all were fabricated at site. And when you enter a power plant site, you will see a big yard which is of the, more or less of the same size as the power plant area, which is dedicated for the steel fabrication. Largely it was a site welded construction because everything happens at field. So everything will be fabricated at site and erected with welded construction. The drawing issuance was happening like say first of all the crane columns of first bay, second bay, then other bay, then the roof system, then crane girder. So it was happening in this fashion. So engineering will also proceed in same line. Earlier like our pioneers in power industry used to like say design only one frame at a time. Then roof at a separate thing. No 3D was happening in big companies up to like say the year 2003 or 4. Okay, so this is how things were happening. Then the job of engineer was to just give the drawings, okay, and some typical sketches of connection. Retailer will simply go to his old ways of doing CAD drafting, create the connections, make the fabrication drawing, and fabrication happens at site. Okay, engineer of course will use it. So you can understand the number of stakeholders in this entire process. Like engineer does his job by issuing the drawing, then there is a retailer, EPC contractor, fabricator, then again we come into picture. So typically construction time, as I said, was 24 to 30 months. What is now the changing trend? Okay, the client has now imposed a lot of things, though we are not very popular or like we are lacking a lot of skilled labor in like some motor construction. We have a lot of limitations on the factory side also. Sometimes we feel there is a mandate for shop fabrication. Client says we want to not occupy the space, so do everything at shop. and simply bring everything at site, assemble it and then erect it. That's how the boarded construction has recently taken the momentum. Like so the plant, if I can say, which we did in like say 2010, was with welded, 2011 welded, 2012 welded, but 2014 onwards, we are doing all the structures in bolts. As you obviously know, why the boarded construction is being preferred is for better quality control, okay, ease of erection, reduce plant space, and of course there is a lot of focus on wastage management because clients don't want to waste money on like say scrap and other things. Of course, for the field welding nowadays there is a lot of focus on like say the safety of people. So in order to do field welding, either the testing of welding or making like say the platform for welding, there is a huge focus on like say the safety aspects. So client also say avoid side weld as much as possible. As I said, schedules, earlier we used to engineer this kind of building in 20 months. Now we have to finish in like say 10 to 11 months. Large portion of the plant building has to be completed. So the time has become half. The construction time has been reduced from 24 to 30 months to now let's say 16 to 18 months. Okay. Now the biggest issue for us is basically the client expectation is increased a grade. They say we don't want to go to many parties. Okay, you give everything to us. Right from engineering, details, application drawing, everything you do, whichever way you are comfortable, we will simply take your drawing, fabricate things, ship it to site and then erect it. So this is the biggest thing we have seen in last 3 to 4 years. There is a complete change in like say the tradition and the logistics. Client says we need to have member sizes which can be shaped. We should have like say the consignment loads. They don't want to make number of trucks more and more to move from shop to the site. So they discuss with us that what will be the truck loading, how you should plan the splices and other things so that it is very easy for them to do the things at site. Of course, erection and connection design philosophy earlier was not anything for focus was given, it will be detailed by the detailer. Nowadays we have to discuss with client, even fabricator, even erector, because how it will be easy for them to do erection. And very importantly now, in order to control the cost, customer asks a lot of data from us, like say member wise quantities, then shipment wise quantities, number of bolts, number of different grades of bolts. All those things are being asked from us, okay, which in otherwise it was not possible. Like say the connection weight, somebody will say it is 14%, 15%, 20%. But in each element, why? Those questions were never asked to us prior to 2010 or so. But of late, in order to compete in market, client asks this type of data. Even like say 1% saving in connection is a very, very big focus. So, as I said, my challenges as an engineer is basically we need to meet the construction schedule in an engineering time given to us about 10 to 12 months. Previously, like say in traditional boarded construction, what used to happen? Everything will be done, complete engineering. The entire package will be given to the retailer. Either he will do on CAD or in Tekla or in other smart software, and then he generates the shop plan. But here, the plant engineering is not like that. You can decide few things, but a lot of things will be decided at a later date. Okay. But in boarded construction, like say a member which is going to be designed and detailed after like say 6 or 7 months, but its primary member is supposed to go along with the column frame. So it has to be engineered or it has to be provided with suitable connections. Okay. So as I said here that we have to plan like a non-engineered item upfront so that we maintain the sequence of erection to meet the project progress. Late availability of equipment data. Like say, in order to create main column frame, roof truss, crane girder, we don't get all those inputs in the first phase. We always get it at a little bit later part. But we still clear, we make a lot of assumptions and proceed with the fabrication. Client, once first lot of fabrication drawing goes, they say no, we need now a different type of connection. We have decided instead of 8 meter now length, we want to go with 6 meter. So you will see a lot of change in splicing location and associated issues. And we need to continuously check and balance the logistics requirement, because once we give the first lot of fabrication drawing, client will check from us, data provided by us, that whether this consignment will be fully loaded in a way which will be most economical for them. So we need to give this type of data. So how we responded to this particular challenge? Because for an engineer like us, who is not part of like say making fabrication drawing or understanding the logistics, how we adopted this particular thing and the need of the hour. So what we did from our past experience of like say supercritical project, we created like say a trend. You can see two very dashed lines, which is actually the progress of fabrication drawing received from a detailer, or how the fabrication happened at site. So those data were obtained from site, and we understood that what is the requirement of site in order to maintain the schedule. Now these two dashed lines are actually reduced span of the work. Earlier I said it was 30 months, now it was reduced to a level of like say 20 months or 24 months. Then you can see two lines, the red and the lavender color. Okay. What we did internally was that how best we can do or how best we cannot do. So we created an internal assessment of this entire data, that if we fail, then it will be the lavender color line. It will be, I would say, pessimistic plan. And the optimistic plan was the red line. So we wanted to play in and around between these two curves, because previous projects were also hovering around those two trends. Finally, I mean, just declaring that this kind of planning, you can see the blue color line, which is our actual performance, and we did better than our rest of these things. How it could happen? Because earlier we thought that the customer will say, I will need about 800 to 1000 ton per month shop drawings. But later when the project started, client said in some months we need 1500, sometimes to maybe like 2500 ton. Okay, so it was very difficult for us to really adapt to this particular challenge. Now, knowing this, I'll just give you a glimpse that what we did. A lot of planning was done here. We divided each and every element and in different sequences. So you can see the gross weight, then sequence 1 to sequence 5, the building was divided into 5 sequences as per the erection scheme. And for each of the sequence, we had like engineered quantities, engineering to be done, RFC drawings approved from client, and how we are working on the fabrication drawing. So we took the challenge on us. We decided we will not go out. We in-house will make the fabrication drawing. Okay, and in the bottom table you can see the database was created right from the beginning for each sequence, each element. I mean, right now you can see about 12 items, but actual Excel sheet is about 40 different items in let's say 5 different sequences. So with a meticulous plan, we knew that what is available for work. And here, like say, we had to acquire skills of making like say fabrication drawing using smart tools. We also adopted the latest technology. We acquired a lot of licenses of Tekla, and you can see here that there was like say optimistic plan, pessimistic plan, and then the best estimate plan. And accordingly, how many people will be required on each month? On like say the capacity of people, like say one person can produce 125 to like say 200 ton per month. That's how the entire planning was conducted. Okay. We also interacted with our stakeholders, erector. There were like say dedicated session at site, in office, with fabricator, with erector, everybody, that what way it will happen. Otherwise, making changes in bolted construction is very time consuming and we don't want to lose the time. Okay. So we had a lot of interaction with our logistics people also. And we also created some new aspects in our engineering. We had to change the process. The way we used to work about 6 to 8 years back, we had to change the process. So what we decided, the first thing we decided that we will not make separate erection drawing. Like say, as you know that we always make like a design drawing which is not having erection mark. Then the detailer will give the erection drawing, and after the erection drawing is approved, the fabrication drawing will generate. What we did here, the drawing which is design drawing was given with erection numbering itself, so that the erection plan was generated simultaneously. Each and every element in a turbine building, and I can just give you a brief that there are about 30,000 different elements to be fabricated. Each and every element was given a different unique number. Because here we had to have like any changes will happen. Some number will be deleted, a lot of members will be added. Okay. So this is the way we used to do, maybe like say 8 years back. This is how the new drawing look like. Okay, the new drawing is with like say double line with all different connections, erection numbering. Okay, so everything is part of the drawing now, and out of which we created the fabrication drawing. And each and every part was also detailed. Lot of data is here, like say you can see month revision by revision how we achieved our targets. So we were able to monitor our performance on a continuous basis. And ultimately the steel construction happened. It is in the project in Madhya Pradesh. Okay, so right now it is under commissioning stage. Building is completely erected, the facades are there, everything is there. Okay. So concluding remarks, primarily like say our time for doing engineering has gone drastically. I mean, it is almost half now. Client expectations are now that everything should come from one shop. They don't want to talk to many people. They don't want to engage their own people also. One who will be expediting with fabricator, one with retailer, one with us. It's all one days. Okay. Better management of changes in fabrication drawing, because things will change in plant at any given point of time. It has to be controlled by one person at a time. Simultaneous engineering and fabrication is the requirement. I cannot say that I will complete my building and then I will issue the fabrication drawing. It is not the case. So it's a big change we are, and of course with planning and innovation we are able to change the trend, and we could achieve, like say the biggest achievement for us was we could reduce the quantity by 7%. When we adopted the shop drawing in our scope, we were much more focused on like say how the connection will be detailed, what weight will be done, and we could achieve about 7%. And you can imagine 13,500 ton, 7% is a big number. So it was a huge saving for us. Thank you.